researchers at the Large Hadron Collider have discovered what could be evidence of a quasiparticle they've been chasing for nearly 50 years. Physicists have been looking for a type of subatomic quasiparticle called an odderon since the 1970s, when it was first theorized. While scientists have previously observed collisions that involve an even number of subatomic particles known as gluons exchanged between protons, the latest findings show potential evidence of an odd number. According to the researchers, the discovery could help to clear up some of the opaque regions in the Standard Model. "We've been looking for this since the 1970s, said Christophe Royon, Foundation Distinguished Professor in the KU Department of Physics and Astronomy. The experiments at the LHC involved scenarios in which the protons remained intact after the collision. In all other experiments before this, scientists detected collisions in which protons exchanged an even number of gluons, which act as the glue that holds quarks together. The protons interact like two big semi-trucks that are transporting cars, the kind you see on the highway, said Timothy Robin, a particle theorist at KU who has worked on the odderon. If those trucks crashed together, after the crash you'd still have the trucks, but the cars would now be outside, no longer aboard the trucks, and also new cars are produced, energy is transformed into matter. Using higher energy and more precise collisions than in the past, the researchers detected possible evidence of an odd number of gluons. The results of the experiments are published preprint on R14 and CERN servers in 2 separate papers. Until now, most models were thinking there was a pair of gluons, always an even number, Royon said. Now we measure for the first time the higher number of events and properties and at a new energy. We found measurements that are incompatible with this traditional model of assuming an even number of gluons. It's a kind of discovery that we might have seen for the first time, this odd exchange of the number of gluons. There may be 3, 5, 7 or more gluons. According to the researchers, the odderon is essentially the total contribution from all types of odd gluon exchange. This includes 3, 5, 7, and other odd numbers. The earlier models assumed contributions from all even numbers, such as 2, 4, 6, and so on. More than 100 physicists from 8 countries collaborated on the experiment, which is now said to add new detail to the Standard Model. This doesn't break the Standard Model, but there are very opaque regions of the Standard Model, and this work shines a light on one of those opaque regions, said Robin. These ideas date back to the 70s, but even at that time it quickly became evident we weren't close technologically to being able to see the odderon, so while there are several decades of predictions, the odderon has not been seen, Robin said. The experiment, dubbed Totem, was designed to spot protons that are not destroyed in the collisions, but slightly deviated. To do this, the detectors are placed at a few millimeters from the beams of protons that did not interact. They then compare the results with previous measurements made at lower energies. If you go to really high energies, there are signatures of the behavior of beams collided at a high energy that can be measured, said Robin. But there are different types of high-energy growth signatures. Up until now, we've only had to think about one type of high-energy growth behavior. Essentially, these quantities might change as a function of the amount of energy. The rho parameter is essentially measuring the ratio of one signature to another of this high-energy growth.